Right now, at this very moment, the James Webb Space Telescope is staring into a region of space so distant that the light reaching its sensors left its source over 13 billion years ago. That light has been traveling through the expanding universe for longer than our sun has existed, longer than our solar system has existed, longer than the Earth itself has existed. And what that light is showing us has left astronomers around the world genuinely stunned. Because James Webb just captured an image of something that, according to every model we have built to explain how the universe works, simply should not be there. I'm talking about galaxies. Fully formed, massive, structured galaxies appearing in images of the universe when it was barely 500 million years old. Galaxies that are too old, too massive, and too organized to exist at that point in cosmic history. And the discovery is forcing physicists to ask a question they really did not want to ask. What if the story we have been telling about the beginning of the universe is wrong? This is Space Horizon, where we explore what lies beyond. If this is the kind of story that makes you see the cosmos differently, hit that subscribe button right now, because we are just getting started. Let me take you back to the moment this whole story began. December 25th, 2021. A European Ariane rocket lifts off from French Guiana carrying the most advanced space observatory humanity has ever built, the James Webb Space Telescope. 6.5 tons of folded mirrors, infrared sensors, and sun shields designed to unfold in the vacuum of space like an impossibly complex piece of origami. NASA, the European Space Agency, and the Canadian Space Agency had spent over $10 billion and nearly 3 decades developing this machine. Its primary mission was clear: look deeper into space and further back in time than any telescope ever has. Find the first galaxies that formed after the Big Bang. Watch stars being born inside distant nebulae. Study the atmospheres of planets orbiting other stars. Answer some of the biggest questions in cosmology. And it has done all of that. But it has also done something nobody anticipated. It found things that were not supposed to be there. By July of 2022, just 6 months after launch, James Webb began transmitting images from a survey called JADES, the JWST Advanced Deep Extragalactic Survey. Scientists pointed the telescope at a tiny patch of sky, no bigger than the size of a grain of sand held at arm's length, and told it to stare. For days, the telescope collected every photon of light coming from that one small region of deep space. What came back were images of galaxies so distant that their light had been traveling for over 13 billion years. These were not galaxies as they appear today. These were galaxies as they existed when the universe itself was in its infancy, less than 5% of its current age. And immediately, something looked wrong. The galaxies were too bright. They were too large, and they were far too well organized. According to the standard cosmological model, the model built from decades of observations, mathematics, and theory, galaxies this early in the universe should be small, faint, irregular blobs of gas and stars just beginning to clump together under gravity. What James Webb found instead were massive spiral and elliptical galaxies, some with structures that looked startlingly similar to the mature galaxies we see in the universe today. One of the galaxies identified in the survey, cataloged as JADES GES ZIF-14 Zizero, was confirmed to have formed just 290 million years after the Big Bang. To put that in perspective, if the entire history of the universe were compressed into a single year, this galaxy appeared on January 2nd. The universe had barely begun, and there it was, fully formed, actively producing stars, and shining with a brightness that should not have been possible. Astronomers ran the numbers again. They checked the instruments, they recalibrated the redshift measurements, the technique used to determine how far away and how old these galaxies are. Everything checked out. The data was solid. The galaxies were real, and they were not supposed to exist. Here is why this is such a problem. The story of how galaxies form goes like this. In the beginning, right after the Big Bang, the universe was a hot, dense, almost perfectly uniform soup of hydrogen, helium, and energy. As the universe expanded and cooled, tiny fluctuations in density, small regions where matter was just slightly more concentrated than average, began to collapse under their own gravity. Over millions of years, these collapsing regions pulled in more and more matter, forming the first stars. Those stars grouped together into small clumps. Those clumps merged with other clumps. And slowly, over hundreds of millions of years, the first galaxies took shape. This process was gradual, messy, and slow. The early universe was supposed to be a construction site, not a finished city. But what James Webb is showing us looks like a finished city. Galaxies with hundreds of millions, sometimes billions of solar masses worth of stars. Galaxies with organized spiral arms and central bulges. Galaxies that, by every model we have, should not have had enough time to assemble that much mass, let alone arrange it into coherent structures. One research team, publishing their findings in the journal Nature, described these galaxies as universe breakers, not because they broke the telescope, because they broke the models. The theoretical framework that has guided cosmology for the last 50 years cannot easily explain what James Webb is seeing. So what is actually going on? Let me walk you through the possibilities, because this is where the science gets fascinating and also deeply uncertain. The first possibility is that our understanding of how quickly galaxies can form is wrong. Maybe, under the right conditions, galaxies can assemble far faster than we thought. If the early universe had regions where dark matter, the invisible substance that makes up most of the mass in the universe, was more concentrated than expected, those regions could have collapsed into galaxies much more quickly. Some researchers are exploring models where the first stars were far more massive than stars today. Massive stars burn through their fuel incredibly quickly and explode as supernovae within just a few million years. If the early universe was filled with these monster stars, they could have produced huge amounts of heavy elements and energy in a short time, possibly speeding up galaxy formation. But even these ideas have limits. You still need time for gravity to pull matter together. You still need time for stars to form, live, die, and enrich the surrounding gas with the materials needed to build the next generation of stars. And the galaxies James Webb is finding seem to have skipped several steps. The second possibility is that we are misinterpreting what we are seeing. Redshift measurements, the primary tool for determining the distance and age of galaxies, rely on understanding how light stretches as it travels through expanding space. If something about the early universe affected light in ways we have not accounted for, the galaxies might not actually be as distant or as old as the redshift values suggest. But this explanation has problems too. Multiple independent methods have confirmed the redshifts. Follow-up observations using different instruments have validated the distances, and the sheer number of these unexpected galaxies makes a systematic measurement error unlikely. The third possibility, and this is the one that has some physicists genuinely uncomfortable, is that something about our model of the Big Bang and the early expansion of the universe is incomplete or incorrect. Maybe the universe did not evolve exactly the way we think it did. Maybe the conditions in the first few 100 million years after the Big Bang were fundamentally different from what our equations predict. This does not mean the Big Bang theory is wrong. The evidence for the Big Bang, the expansion of the universe, the cosmic microwave background radiation, the abundance of hydrogen and helium, all of that still holds. But the details, the precise sequence of events in those first few 100 million years, might need revision. And revising cosmological models is not something scientists do lightly. These models are built on decades of observations from multiple telescopes, particle physics experiments, and theoretical work. Changing them requires extraordinary evidence, but James Webb is providing evidence that is hard to ignore. One of the most talked about hypothetical solutions involves reconsidering the role of dark energy, the mysterious force driving the accelerated expansion of the universe. If dark energy behaved differently in the early universe than it does today, it could have affected the rate of structure formation in ways current models do not account for. Another idea involves primordial black holes, theoretical black holes that could have formed in the very first moments after the Big Bang. If these black holes existed and were more common than we thought, they could have acted as seeds around which matter rapidly collected, jump-starting galaxy formation, much earlier than gravity alone would allow. These are speculative ideas, but the fact that serious scientists are seriously discussing them tells you how significant the James Webb findings really are. Now, let me give you some specific examples, because the numbers behind these discoveries are staggering. In early 2024, a team led by researchers at the University of Edinburgh identified a galaxy designated as JADES GS-Z13-0. This galaxy formed approximately 325 million years after the Big Bang. Its estimated stellar mass is around 1 billion times the mass of our Sun. Think about what that means. In just 325 million years, enough gas had to collapse, ignite into stars, and assemble into a structured galaxy containing 1 billion suns worth of material. According to standard models, building that much mass in that little time pushes the limits of what gravity can accomplish. Another galaxy, found in a separate survey called CEERS, the Cosmic Evolution Early Release Science Survey, showed signs of a supermassive black hole at its center. Supermassive black holes, the kind that sit at the hearts of galaxies like our Milky Way, are thought to grow over billions of years as they consume surrounding matter. Finding one in a galaxy barely 400 million years old raises the same question. How did it get so big so fast? Some researchers have proposed that these early supermassive black holes did not grow from the collapse of individual stars, the usual formation pathway, but instead formed directly from massive clouds of gas collapsing in the early universe. If true, that would represent a completely different mechanism for black hole formation that we have never directly observed. The data keeps piling up. As of mid-2025, James Webb has identified over a dozen galaxies in the first 500 million years after the Big Bang that challenge existing formation models. Each new observation adds another piece to a puzzle that does not yet fit together cleanly. And this is where I want to pause and talk about what this means for science, because I think this moment is important. A lot of people hear stories like this and think it means science is broken, that scientists do not know what they're talking about, that everything we have been taught is wrong. That is not what is happening here. What is happening is exactly what science is supposed to do. We build models based on the best available evidence. Those models make predictions. We build better instruments to test those predictions. And sometimes those instruments show us something the models did not predict. When that happens, we do not throw out everything we know. We refine the models. We ask better questions. We look for new explanations. The discovery of the galaxies that formed faster than expected does not invalidate decades of cosmology. It tells us there is more to learn, and that is exciting, because it means the universe is stranger, more complex, and more interesting than we gave it credit for. James Webb is still in the early years of its mission. It is designed to operate for at least 10 years, possibly longer if the fuel and instruments hold out. Every month, new data arrives, new images are processed, new papers are published, and each one adds a little more detail to the picture. Right now, teams of astronomers are using James Webb to study the chemical composition of these early galaxies, looking for clues about what kinds of stars formed first and how quickly they enriched the surrounding gas with heavy elements. Other teams are measuring the sizes and shapes of these galaxies in finer detail, trying to understand how their structures formed. There is also a major effort underway to identify even older galaxies, pushing back to within 200 million years of the Big Bang, maybe even earlier. If James Webb can find galaxies that formed in the first 100 to 200 million years after the universe began, that would put even more pressure on existing models and give scientists crucial new data to work with. Some researchers are calling this the golden age of cosmology, not because we have all the answers, but because we finally have the tools to ask the right questions. James Webb is showing us the universe as it really was in its infancy, not as we theorized it should have been. And the gap between theory and observation is where the most important discoveries happen. So where does this leave us? The honest answer is, we do not know yet. The galaxies James Webb found are real. The data is solid, but the explanation, the reason these galaxies were able to form so quickly and grow so massive, that is still an open question. It could be that galaxy formation is more efficient than we thought. It could be that dark matter was distributed differently in the early universe. It could be that supermassive black holes formed through pathways we have not fully understood. Or it could be that something about the conditions in the early universe, the density of matter, the behavior of dark energy, the rate of expansion, was different in ways our current models have not captured. The answer will come from more observations, more data, and more time spent analyzing what James Webb is sending back. This is not a mystery that will be solved in a single paper or a single year. This is the kind of problem that will define a generation of astronomers. And here's what I want you to take away from this. Right now, 13 billion light years away, there are galaxies that existed when the universe was just a fraction of its current age. Those galaxies formed under conditions we are only beginning to understand. The light from those galaxies has been traveling through space for longer than the Earth has existed, and it finally reached the mirrors of the James Webb Space Telescope just a few years ago. What that light is telling us is that the universe does not follow our rules. It follows its own. And every time we think we have figured it out, every time we think the models are complete, the universe shows us something new, something unexpected, something that challenges us to look harder, think deeper, and ask better questions. That is what makes this discovery so extraordinary. Not because it breaks science, because it pushes science forward. If you want to follow this story as it develops, subscribe to Space Horizon right now, because James Webb is just getting started. Drop a comment and tell me, what do you think is the most likely explanation for these early galaxies? Faster formation, measurement error, or something fundamentally different about the early universe? I read every comment, and I genuinely want to know what you think. And here's something you can do this week. Go outside on a clear night, look up at the stars, and remember that some of the light hitting your eyes left those stars thousands of years ago. The universe is not just vast in space, It is vast in time. And every photon carries a story. Thanks for watching Space Horizon. I'll see you in the next one.